This is the introduction of the overall for the project. Sustainable building materials are the materials that are produced or sourced locally. It have a lower impact on environment and are thermally efficient. Most of the materials contain recycled and industrial waste material and byproduct. On the other hand, the use of sustainable construction materials helps save the budget because the cost is lesser than normal building materials. It also gives out a productive working environment because the materials used are safer. Bricks is a type of block that is used in construction fields such as construction of residential house, walkways, and even retaining walls. These construction materials are known as one of the best materials as it is durable, beautiful, energy efficient, and sustainable. For this project, our group have chosen brick as our sustainable material. Next, I'm going to present my article that I have chosen for this project, which is Physico-Chemical, Mineralogical, and Microscopy Evaluation of Sustainable Bricks Manufactured with Construction Waste. The demand for bricks in building industry used in construction are high, especially the various types of conventional ceramic bricks. The production of this type of bricks require baking of virgin clay in an oven at high temperature which affect the environment. Therefore, the search for alternative ways that can reduce the environment impact is a priority. The materials are those that is recycled second-generation materials from construction and demolition and processes that does not require baking. The use of CD aggregates together with ordinary Portland cement or fly ash does not affect the compressive strength. In another way, CD waste, wood residues, and water cactus pulp extract were used to manufacture and unbaked clay bricks. In addition, blast furnace slag as well as kaolin and granite basalt residues have also been used as a replacement clay to manufacture baked bricks. For the test conducted, the heavy metal concentration are acceptable, where a direct relationship between the increase in VFX content and the compressive strength, and also an inverse relationship with absorption. Other materials that are used in the replacement of bricks are soil and sand of petroleum effluents that is mixed with stone materials. Special cases such as the use of mixture of organic materials such as sawdust, oil-polluted soils, compost, and marble have also been studied. The results stated that the compressive strength, porosity, and absorption are still appropriate for the construction. The use of additive in the manufacture of porous and lightweight clay bricks shows an adequate thermal conductivity and compressive strength. For example, the use of paper waste. In another study, manufacture of bricks using quarrying and mining materials shows that their physical and mineralogical characteristics can be considered comparable to those that has been manufactured with conventional material. Therefore, the search for alternative ways of secondary materials to replace the non-renewable materials in the manufacture of bricks are necessary. The use of all materials above will lead to a lesser environmental impact. The way they conduct the research for the mixtures design, in this stage, 2 dosages and the use of water or water plus mucilage and the differential use of only concrete or all-in-one were investigated. These variables are used because in previous study, it has been determined that the use of mucilage influences the resistance of the bricks. AIO is produced in a higher volume and it has no application in solution. Hence, it will make the AIO as a useful material. For the nomenclature for the mixture, X, XX, X was used. The first X refers to control trial or also known as reference. XX are known as OC or AIO that are used, and the last X refers to the use of water or mucilage. The next stage is the sustainable brick manufacturing process, where the solid materials were manually mixed until they were homogeneously integrated. After that, 2/3 of the liquid's components were added to the mixture and it is allowed to rise for 10 minutes for it to go through a hydration process. The materials are then mixed until it reaches uniform consistency. The remaining liquid component was added lastly until the suitable handling consistency was achieved. When the mixture is ready, it is placed into the brick making machine. The process consists of an initial manual compaction of 3 layers that have a thickness approximately 2 cm each. A second manual compaction was performed after the first manual with the cap of the molding machine. Once the process are complete, the bricks are taken out using an extraction level. Next, the brick will out for drying process for 3 days. To quicken the drying process, the bricks are introduced to solar desiccator. Data were recorded after the initial external drying, and reading were performed every 30 minutes during the maximum solar intensity period, which is around noon time. The temperature and solar radiation are also taken during this stage. A thermocouple thermometer and a sensor with pyrometer were used to determine the temperature and the solar radiation. This process will take around 2 days or after a constant weight was obtained. The next stage is for brick specification and test procedure. In this stage, a compressive strength test and initial maximum water absorption test were performed. A manual compression machine was used for compressive strength test and it is conducted during the day 14, while a mercury thermometer was used for water absorption test during day 28. The scanning electron microscopy was used to characterize the matrix of the resulting materials. Then the chemical composition of the sample was determined through the detection of basic compound using the microanalysis technique with an energy dispersive spectrometer that is connected to SEM unit. To correlate the mechanical, chemical and resistant behavior, a thermal gravimetric analysis was performed. From this, a data acquisition system that automatically records the weight and temperature of the samples are obtained. Meanwhile, the sample used for the TGA study were obtained from manually crushing untested bricks. The particle size are then determined. This is the finding where the first one is the brick drying by solar radiation. We can see the weight loss evaluation and next volumetric matrix. And the next finding is for the compressive strength and the initial maximum exhibition. In the picture, we can see that the grey bar refers to compressive strength, blue bar refers to mixture with OC or IO with addition of mucilage, and then comparing both mixture, VAIOM is 22% more resistant than VOCM. Meanwhile, the orange tilted shows the absorption variation of the samples that use water or mucilage. The use of mucilage generates identical deviation, and OC shows a 52% lower absorption capacity than AIO. Next is for the thermal gravimetric analysis. You can see the weight loss versus temperature increase. Next is the thermal gravimetric analysis of AC, and B is the TGA of AIO. And lastly, figure 9 is the weight loss ranges for different materials. That's it for me. Thank you.
One of the most difficult issues that humanity has today is finding a realistic and viable solution to the trash created by the industry. So, the concept of sustainable and circular economy as well as environment stewardship should be prioritized in contemporary development. This is, therefore, intriguing the employ various industrial waste in the production of various construction material such as ceramic clay brick. The ceramic sector has a great potential for industrial waste reuse and recovery. The manufacture of sustainable clay brick using the waste from secondary aluminium recycling as raw material. So, aluminium is the world's most used non-ferrous metal with a current annual consumption of 24 million tons and one of the most plentiful material in the Earth crust. So, one of the pro of using aluminium is that recycling does not damage the structure of the metal itself, and it can be reused and recycled indefinitely without detracting from its quality. The aluminium recycling industry produces aluminium filter dust, as known as AFE, a waste byproduct of the aluminium recycling process, composed mainly of aluminium oxide in the percentage between 60 to 70%, 8% of calcium dioxide, and almost 15% sodium chloride, and between 5 to 10% of potassium chloride. Due to its aluminium content, this waste can be used as a raw material in the manufacture of ceramic brick, but at the same time reducing the environmental impact produced in the landfill. So, in this study, we'll be going to explore the demand for the secondary aluminium that will be experiencing the annual growth rate of 5% twice in the next few years from now. Therefore, the generation of waste from the second melting of aluminium will also grow, and it is necessary to work on trying to address this type of waste, because otherwise the landfill will be filled and there will be no space to deposit them. The characteristic and incorporation of the waste in the aluminium industry as raw material in the manufacture of construction material has been studied by different authors. So the objective of this research is to assess and to determine the potential use and the possibility of burn brick in construction industry. Secondly, this research also to evaluate the feasibility of employing wasted from the aluminium secondary industry, namely as aluminium filter dust (AFD), a residue that have not previously been examined as a raw material as the substitute for clay in the manufacturing of burnt brick. So we're moving forward to the metal section. So in material, we will be using clay and aluminium filter dust as a raw material. The clay was obtained from the clay quarry, and it is a mixture of three types of clay in different proportion. 40% of black clay, 30% of red clay, and 30% of yellow clay. The waste used is AFD, which is aluminium filter dust, generated in a blast furnace during the manufacture of secondary aluminium. So, as you can see, there is a figure for our clay and the aluminium filter dust. The C is the aluminium filter dust, and the AB is the photo of black, yellow, and red clay. For the processing method, the raw material will dry in a stove at 105 degrees Celsius for 24 hours. Then the clay underwent a process of grinding by means of a ball mill to crush them and reduce their particle size. Both the clay and the AFD were sieved until they reach a particle size less than 150 micrometer. The different proportion of AFD waste were added to the clay. The quantity used for both raw material as well as the nomenclature used for the different proportion as listed in the table below. So as you can see, there is a few brick series which the table of mixture proportion of raw material for brick manufacturing. So we can see a 100C brick series is a mixture of 100% of clay and 0% of FDA. Secondly, we can see 95C to 5 FDA brick series is a mixture of 95% of clay and 5% of FDA, and the list continue. So the brick series available until 75C till 25 FDA, which is the mixture of 75% of clay and 25% of FDA. All of the raw material were whipped and mixed. To convert the plastic property into the mixture, 8% of water was added to the kneader and mixed homogeneously. The obtained mixture was introduced in a rectangular metric of size 60 mm, 30 mm, multiple to 10 mm. So the ceramic pieces were dried at 105 degrees Celsius for 24 hours using an oven in order to eliminate the moisture content and reduce the appearance of the crack. The specimen were fired using a Navitum furnace with a heating rate of 2 degrees Celsius per minute and the final temperature of 950 degrees Celsius, maintaining this temperature for 1 hour. The fire brick will cool down to the room temperature. Finally, this is the method for a comparative method for 10 sample per series was produced using all the raw material, which is the clay and the AFD, aluminium filter dust. So next we will be talking about the findings, so the result on the characterization of raw material. So as you can see, the table of chemical composition of clay and aluminium filter dust. The chemical composition of clay mixture and the AFD is determined by the XRF is shown in the table. What is XRF? XRF is an X-ray fluorescent that help in identifying the chemical composition. High amount of quartz 54.4% was a predominant oxide were detected in the raw clay, along with aluminum oxide, 12.36%. This can be mainly attributed to the aluminosilicate in the clay. The relevant proportion of oxocalcium, 8.76%, could be derived from the high presence of carbonate, as indicated from the loss of ignition observed. The chemical composition of AFP shown considerate amount of aluminum oxide, 21.56%, and alkaline earth oxide, sodium oxide, with potassium oxide in 5.58%, and a smaller quantity of ferric oxide, 0.64%, also calcium, 1.31%, and magnesium oxide, 2.37%. The large amount of flux oxide in the waste could decrease the firing temperature or the time of the ceramic brick, saving energy in the process. Loss of ignition at 950 degrees Celsius was 21.82%, probably attributable to the less effective combustion or thermal decomposition of the inorganic species. So take a look on the thermogravimetry and differential thermal analysis of a raw clay and AFD waste. So a thermal behavior of clay and the AFD residue is shown in figure 3, with loss of 1% at the temperature between 30 to 150 degrees Celsius was observed, with an endothermic peak center at the approximately 85 degrees Celsius attributed to the loss of moisture. So at temperature, as you can see in the figure A, at temperature between 100 to 600 degrees Celsius, 2.2% weight loss was observed, associated with the combustion of organic matter and the dehydration of clay material, as indicated by the exothermic peak center at 375 and 475 degrees Celsius, and the endothermic peak center at 570 degrees Celsius respectively. So between 600 and 800 degrees Celsius, a weight loss of 8.2% was produced and is assigned to the carbonate decomposition. Between 8 till 100 degrees Celsius, two exothermic peak center at 825 and 915 degrees Celsius were observed. This associates with the crystallization of the high temperature phase. So the total weight loss of the clay in the first figure was 11.2%. So next we will be talking about the thermal behavior of the AFD waste shown in the figure below. So the total weight loss of the aluminium filter dust waste was 48.3%. The weight loss between 30 till 150 degrees Celsius was 1.3% because of the water evaporation. So between 1 till 150 till 375 degrees Celsius, a weight loss of 4% was observed due to the combustion of organic matter, as indicated by the exothermic peak center at 275 degrees Celsius. So as you can see here, the thermodifferential analysis curve present two endothermic signal centered at 475 degrees Celsius and 675 degrees Celsius. It both was due to the crystallization during the heat treatment. So as you can see, all the exothermic and the endothermic was happened due to the crystallization during the heat treatment. The greatest weight loss of 38% occurred during the 750 to 1175 degrees Celsius due to the carbonate decomposition and the crystallization of phase, such as the silicon and aluminum spine prior to the melted phase, as indicated by the exothermic peak at 775 degrees Celsius and the endothermic peak at 986 and 1130 degrees Celsius. Next, we'll be talking about the bulk density and water absorption of fire brick as a function of EFD waste content. Water absorption by the capillarity can significantly affect the durable and the quality of the brick. The bonding of brick with the mortar depends on a large extent on the water absorption by the capillarity capacity of the water in the brick and the water retention power of the mortar. Low value of water absorption. The capillary in the brick contribute to a good durability and consequently greater resistance to the environment. For brick and water absorption, the capillary action greater than 1.5 kg per m square minutes, it is recommended to moisten them before they are laid. Thus, the brick must be moistened to ensure proper mortar curing. So we can see based on the graph here, the water absorption of control brick was 13.6%. The incorporated up to 20% of waste produced a slight increase in water absorption, reaching a value of 14.7%. Greater additional of EFD waste up to 25% produced 75C25 EFD brick with a higher value of water absorption, increasing this property until reach 20.9%. The content of gases, organic matter content was 2.2629% and 8.9%, and that of the carbonate was 77.36% and 18.1%. The AFD waste contain a higher content of both flux material and gaseous compound. The incorporation of the AFD waste into the clay body produces both of information of molten material at a lower temperature that tends to compress the pores and gases component, which generate gases and swell the ceramic body during the firing process. So, according to the ASTM C6703, the maximum value allowed for several weathering resistant ceramic brick for construction is 22%, and hence all the series produced comply with the standard. The compressive strength of ceramic material is the most critical engineering property for building material. The compressive strength value of the control brick was 39.6 MPa. The compressive strength of the brick was determined by the porosity, which is the number, type, and the size of pore in the body of the brick. According to the water absorption study, the open porosity of brick containing up to 20% waste is comparable to the control brick with a slightly higher proportion of smaller pores and a little more compact structure. This distribution of porosity improves the compressive strength of the brick. However, the additional 25% of residue produces a greater open porosity and a larger open of smaller pores that can act as a stress contractor, resulting in a low compressive strength.
Interaction due to problems with the manufacture of building materials that contribute to greenhouse effect, the construction industry and the building environment frequently become important issues. Clay bricks are made by heating a dry mixture of clay, coal, and water inflamed at temperature ranging from 700 to 1100 degrees Celsius. The process creates a lot of carbon dioxide and requires a lot of energy. Okay, so the significant carbon emission is related to the brick's high curing temperature, which improve its characteristic and make it more compatible with other materials. With the growing need for housing units and as a result, wall material in many parts of the world, as well as the growing demand for environmentally friendly building materials, it is critical to add eco-friendly features into bricks. The ability to source through environmental conservation, and items that do not generate harmful waste is one of the characteristics of sustainable building material. Products that can conserve energy of water while also contributing to a healthy and safe environment are also classified as sustainable construction material. Painted cellulose fiber are an agricultural waste product that cannot be fully exploited in brick manufacture unless the brick meets particular specification and meet relevant regulation. The result, focus of the study is on the qualities of eco brick made from plant trunk cellulose fiber. So, the objective of this research are to investigate the impact of plantain fiber and master greenham Sky 504 on the quality of eco brick in order to improve our understanding of brick option for construction projects, and to analyze the influence of this plantain fiber and Sky 504 on bulk density, competitive strength, and water absorption of brick specimen in the construction of eco brick. The method that used in this research are mixed design. Okay, for the first step is the bricks were made with 1:3 cement to sand ratio, a variable percentage of banana fiber, and 0.015% Sky 504 cement. The mixture aggregation was served, and the goal mean strength was calculated using a 1/3 mixing ratio. And the second step, the quantities of the material mixture utilized for the group, as well as the code for each brick sample are shown in Table 1. And third step, this mixture has been chosen to provide the best mortar that will allow for good work production at a reasonable cost while also providing adequate durability. The water to the cement ratio is 0.3. And fourth, for compression and water absorption test, 12 bricks with the dimension of 225 mm, 112.5 mm, 75 mm were placed for each type of brick for different curing duration. Last but not least, first bricks were carefully crushed on the mold with steel rods, and the mold was given a reference number to make the bricks easier to identify. And lastly, after 24 hours, the mold was removed and the pool curing process was used, in which the bricks were totally immersed in water throughout the curing period. And this is the table 1, which is mixed proportion. Based on the graph beside, the bulk density reduced as the amount of the plantain fiber content increased according to the findings. Okay, this property may be related to the lightness of the plantain fiber in the mixture. Okay, in this investigation, the bulk density of the reference sample was higher than the control sample because of larger mixing ratio was utilized in this investigation. Okay, specimen with Sky 504 but no fiber, on the other hand, exhibited a 0.03% higher bulk density than the control sample. In table 2, it shows a decrease in composite strength of ecobrick with increased plantain fiber at 0.015 grimium Sky 504 plasticizer and 0.3 grimium Sky 504 plasticizer. Okay, table 2 reveals that the average mass of EBC is 4.40 kg, while the average mass of ecobrick made with 2% plantain fiber is 4.18 kg. There is partial drop in ecobrick mass with an increased plantain fiber. Based on table 3, partially demonstrate a decrease in compressive strength of ecobrick with increase in plantain fiber. Okay, in this table also show the reverse, that the average mass of ABC is 4.55 kg, while the average mass of ecobrick made with 2% plantain fiber is 4.20 kg. With the additional of plantain fiber, there is a partial decrease in the mass of the ecobrick. The table also reveals that the mass of the ecobrick increased significantly as the curing period increase. Showing is that the sample continues absorb water from the content throughout the first 7 days. For table 4, at 0.015 granium Sky 504 elasticity and 0.2 water estimate ratio, the average result of sample 7-day compressive strength test reported in table 4 partially demonstrate a decrease in compressive strength of the ecobrick with increase in plantain fiber. Okay, table 4 also shows that the average mass of EBC is 4.5 5 kg, while the average mass of eco brick made with 2% plantain fiber is 4.20 kg. With the addition of the plantain fiber, there is a partial decrease in the mass of the eco brick. The graph shows that the compressive strength of eco brick is a function of curing time. The pace of strength development among the eco brick varies as does the period of curing, as seen in the graph. In addition, when compared to the control eco brick sample ABC, plantain fiber reinforced eco brick with 0.5%, 1.5%, and 2% plantain fiber reinforced eco brick shows similar increase in rate of early strength development. In this table 5 shows that the water absorption value of the eco brick ranged from 4.76 until 7.899 according to BS 3921 9845. The water absorption of brick for building work should not exceed 4.5% by mass and should not exceed 7.0%. According to the table 5, the water absorption of the control sample ABC is 7.14, where EB1 is 594, EB2, EB3, EB4, and EB5 are 6.02, 6.25, 7.89, and 4.74 respectively. The results suggest that the addition of beam sky 504 to EB1 reduces the water absorption, resulting in a lower water absorption value than the control sample ABC.
There is some comparison that we can make based on these three sustainable brick. Firstly, plantain fiber brick. They compare the compressive strength of this eco brick increasing as the curing period increase. The rate of the strength development among the eco brick differs with the duration of curing. The compressive strength developed with age as the fiber content increasing up to 1.5% fiber content, but reduced if the fiber content beyond 1.5%. So from the density, plantain fiber brick decrease with an increase in the fiber content. There is a decrease in the mass of the specimen at equal volume, resulting to a decrease in density of the specimen. So from the water absorption, plantain fiber brick is a characteristic increasing in water absorption as a result of increasing in void within the eco brick. The water absorption value of the eco brick produced from 0.5, 1.0, 1.5%, and 2.0%. Enough fiber increasing as the fiber content increase. The water absorption decrease as the mass after the oven drying increasing. For aluminium filter gasifier brick, compressive strength. The compressive strength value of the control brick was 39.6 MPa. The additional of 20% in waste resulting in higher compressive strength value more than the control brick, but the incooperative of 25% of waste produced brick with a pronounced decrease in the compressive strength of up to 18 MPa. So from the density of aluminium filter gasifier decreased with an increase in the AFD waste. The bulk density of control brick was 2534 kgm squared, decreasing by 2.17% and by 12% when 5% and 25% of AFD were added. This could be attributed to the lower relative density of the AFD residue compared to the clay. So from the water absorption, they increase as the AFD waste increasing. The AFD waste contain a high content of both flux material and gaseous compound. The water absorption of the control brick was 13.6%. This increase could be a sequence of a chemical composition of the clay and the AFD residue. For the construction waste brick, for the compressive strength, they comparing both mixture V, AIOM is 22% more resistant than VOCM. The OCM shows that the 52% lower absorption capacity than AIO. The use of Muley gauge generate identical deviation. So for the density, construction waste brick increasing construction waste brick density increasing as the profile and volumeric weight of the crush sample increase as well. The samples are having a similar volumetric weight, therefore it can be concluded that they went into the same process. For the water absorption, construction waste break water absorption increasing as the weight loss caused by the break desiccation increase. The drying process for all the samples in this research are almost similar.
For the critique based on this question, which is how well the studies address the research question, were there any limitation? Okay, the answer of this question is each question can be answered well based on the study complete by clearly demonstrating the methodology and findings in the paper. This test which was done in the article shows that even with recycled aggregate, it's possible to produce bricks that are both sustainable and economically effective. And for the question for the how accurate were the result? Are any of the result convincing? Okay, the result for both are really remarkable with the quantity of data and graphic they provide from one test to the next test, increasing the reliability of the result and data. In order to make the article more informative, some information have been included. The result for the two articles also differ, since they are depend on the specimen size and type of employee in the study. Next, for the question, what aspect of the research works were unclear? Okay, there are no component of the research effort that are uncertain based on both viewpoints. This is due to the large number of tests that they are able to complete successfully. In addition, one of the articles includes picture of photo to make it more enjoyable to read. And for the last question, how does the study going to contribute to development of future sustainable product? Okay, contributing to the development of future sustainable product can preserve the environment. According to this study, it is due to the fact that the mining procedure for this aggregate is not eco-friendly. Okay, each year the need to modify the soil, kill indigenous flora and fauna might treat to the nature. In addition, transporting material to brick making factory is costly and often result in greater greenhouse gas emission. Not only will employing recycled aggregate for brick manufacture help to conserve natural aggregate resources and reduce greenhouse gas emission, but it will also save money for the construction sector.
As for conclusion, the use of construction waste for the manufacture of sustainable bricks not only can be environmentally friendly, but it also technologically feasible alternative. This is because the materials that are residues and no thermal backing is involved during the manufacture. The objective of this project has been achieved. Students are able to perform knowledge and understanding of well-established materials effectively. For example, students know that the use of fly ash does not significantly affect the compressive strength of the concrete bricks. Then that the use of filter dust in the aluminium as the raw material during manufacture of clay bricks also leads to better bricks as it lessens the environmental impact, but still serve a high compressive strength and low thermal conductivity. These types of bricks can be considered almost the same as the normal bricks. In addition, the results from the research made are convincing as it shows the data from all the tests conducted. From the data itself, we can determine the compressive strength, bulk density, porosity, and etc. This data has helped to convince students in doing the research. Therefore, taking into account of the result exposed in this project, the alternative materials can also be used in the manufacturing of sustainable bricks. However, further study or research are necessary to make sure that all the materials are safe to use as replaced in the manufacture of bricks.